All right, returning to problem number 34. For this group of problems, we want to find the vertical asymptotes, if any, of the graph of the rational function. So what we need to remember is that language, vertical asymptotes, means let's look at the denominator. Let's set the denominator equal to 0. But also paying attention to the numerator so that in case we have any common factors with the numerator and denominator, we know that we don't have a vertical asymptote. We have a hole at the x value of that common factor. So mainly looking at the denominator, but we also want to keep in mind the numerator as well. All right, so find the vertical asymptotes, if any, of the graph of the rational function. All right, I think I'm going to have to do this on paper, so let me get some of that here. All right, vertical asymptotes, let me start with the denominator. I noticed the numerator can't be factored, or, I mean, it's just x, there's nothing to do there. Set the denominator equal to 0. To solve this, I'll probably, because I'm missing a linear term, subtract the 7 to the other side. And what happens is we get x squared equals -7. Well, there's not any number that we can square and get a negative answer. So this is really going to be no solution, but the algebraic work that would support that is let's bring in the square root. And as soon as you put that square root over that negative number, that tells us that we're out of a real solution situation. We can only have imaginary numbers. So this would come out as an x between absolute value, but this is an I, an imaginary situation. You could pull the negative out as an I and put I squared to 7, but that symbol just means there's no solution. So how do we respond to the question if we were asked to find vertical asymptotes? Well, there is no x that would make your denominator 0 without your numerator being 0. So we're just going to say no vertical asymptotes. Okay, so for this one, I might try and factor the denominator. So I can see that that's going to factor x minus 2 and x plus 2. And so before I set the denominator equal to 0, I'm going to look for common factors, because common factors tell us we don't have vertical asymptotes, we have holes. And think about grouping the numerator into its own parenthesis. And I see that x plus 2 would divide out with x plus 2. Those are little ones. So that tells me that I have a hole at the 0 of that factor. So in the 0 of this factor is -2. So at x equals -2, I do have a hole. They're not asking me to discuss the hole. They're asking me to discuss vertical asymptotes. So the remaining factor should be set equal to 0. And when you do, you're going to get x equals +2. And because I don't cancel that with the numerator with another common factor, that is your vertical asymptote at x equals 2. Okay, so let's look at 36. Hopefully I have enough room here. Make sure I'm on the screen still. Okay, I think I'm going to try and factor the denominator. I can see that even if I do factor the denominator, I'm not going to get one of the factors that matches x minus 9. But I'm still going to go ahead and try and factor this. So factors of 24 that sum to -10. Well, 4 and 6 multiply and give us 24, and if they're both made negative, they would add to -10. Let's set each factor equal to 0. Add the 4, so you're going to get a +4. And then x minus 6 equals 0, so x equals 6. So I had x minus 4, x minus 6, neither of which canceled with the numerator, so both of these are going to be the x values of our vertical asymptotes. They're going to be the equations of our vertical asymptotes. X equals 4 and x equals 6. So just remembering that vertical asymptotes mean to consider the denominator and what's going on there, but also keeping in mind that we're looking for holes as well. All right? All right, 37 and 38 says, solve the polynomial inequality and graph the solution set on a number line. Express the solution set in interval notation. So we're looking for x values that make this quadratic right here, this number, be less than 0. Or for this problem, what values of x when I plug in here, what numbers for x when I plug in here will give me a number that's 0 or higher. So we'll just do one of them, leaving the other for you to do, and then consult the key too. So I guess I'll look at 38. All right, so how do we solve that polynomial inequality? Like, what's our first step? How do we enter into this problem? Let's see if I can get that up here. Well, I believe the first thing we did is we set the polynomial inequality to 0, or set one side equal to 0, which is already done. Then we factored. So let's factor this polynomial, or this quadratic, into two binomials. So factors of 30 that add to 11, that would be 6 and 5 if we did a factor sum chart. And then we actually went ahead and looked at the related equation. We changed from an inequality to an equal sign because we're looking for what we call boundary points. So I'm going to set each factor equal to 0. I'm going to subtract the 6 and subtract the 5. And so then we came over here and we built a number line. And we put those boundary points in the correct order. Remember, negative 6 is less than negative 5. It should go on the left. And I'm trying to think. I think we put a 0 above here and a 0 above here. And then what we did is we did test values. Meaning we went back to maybe our factored version here instead of our original version here. And we chose a value, x value, a test value less than negative 6. Let's say negative 7. And we plugged in negative 7 here and negative 7 here. Of course, you could plug in negative 7 for these x's, but the factored version is easier to kind of analyze. But if x is negative 7, then you add 6, you're going to get a negative. I don't care what the number is, I just care that it's negative. If I put that same negative 7 in here and added 5, that's also a negative. So a negative times a negative, because that's what I'm doing, multiplying, returns a positive answer. So any test value that's less than x equals negative 6, whether it's negative 7, negative 8, negative 9, when you replace those test values in this interval, you're going to get a positive answer. I'm going to plug in negative 5.5 because that just seems like kind of the logical choice between here and here. Negative 5.5. So negative 5.5 plus 6, do it on your calculator, that's positive. Negative 5.5 plus 5 is negative. So positive times negative is going to return a negative. Now, my test value over here in this interval is going to be 0. I know 0 is far away from negative 5, but 0 is to the right of negative 5, and it's easier to work with. So if I put a 0 here and a 0 here, I'm going to get two positive numbers that when multiplied returns positive. So this number line just organizes our work. It's not our solution number line. Okay, so what is our solution? Well, we either have to choose the positive solutions or the negatives, and it's all connected back to the original problem. We're looking for greater than 0 or equal to 0. And you know, I probably should have just filled these in. I'm so sorry. These are filled in circles because I have the or equal to right here. Maybe you were thinking that, and we can certainly do that right here, right now. So I want the positive solution, so I'm going to actually look at changing this to another number line and putting the solution on that number line. So anything positive, so I'm going to come up here and darken this part of the number line and then put a bracket here so I can include the negative 6 because it's or equal. And then the other positive solutions start at x equals negative 5 and continue to infinity. And then from here, my interval notation answer is going to be negative infinity up to negative 6 with a bracket, union. And then we start again at negative 5, and we go to positive infinity. Okay. So you might want to try the other one on your own and then consult the worked out solutions for that. Otherwise, I'll have office hours before the final exam, and we can certainly visit there and discuss further. Okay, 39 and 40, that's strictly on your calculator. We're making sure you know how to use your calculator and the correct keystrokes. Just check the solutions for those. 41 and 42. Back to graphing, looking at exponential functions. You might remember exponential functions have a numeric, a number base, and a variable, or the x, is the exponent now. So if we're going to use the graph of f of x equals 2 raised to the x, that exponential, to obtain the graph of g, We're returning back to those earlier problems where we had to do transformational graphing. So let's just do one of these. We'll do 42. They're both the same, just different transformations. All right, so I'm going to start with my base function, so to speak, of 4 to the x, and then looking at the changes in the g equation, I'm actually going to take that base function that I graph here, and I'm going to move it left 3 and then up 2. So I'm going to need some space here, so let me return to some notebook paper, and we're looking at 42. I'm going to come over here and build my coordinate plane. Okay, if you've forgotten what 4 to the x looks like, you can always create a t-chart. You might remember we created t-charts often where we chose, kind of common practice, to use these x values. It kind of gives us a peek into the function and what's happening on both sides of the y-axis. So if you can't quite remember what that function looks like, you can take turns plugging these values in and getting kind of a basic shape. But with this exponential, I always think that if x is 0, then my output, anything to the 0 power, is 1. So this is 0, 1. If x is 1, then if x is 1 right here, then I'm going to go up to 4. Ooh, I'm going to come off the screen pretty quick. If x is 2, I'm going to be up at 4 squared, or 16. So this graph rises pretty steeply. It's an exponential that grows like this. So what happens over here at x equals -1 and x equals -2? Well, you're going to get very small numbers, and the graph comes back in this direction. We have a horizontal asymptote at y equals 0, so this part of the graph will never touch the negative x-axis. It just gets closer and closer to the x-axis. The points get closer and closer to 0. And then from here, we can just think about our transformational graphing, and we're going to move this graph left 3 and up 2. So I might choose this point. It's a pretty good starting place. Let's move this point left 3 and up 2. So left 1, 2, I need one more, and then I'm going to move it up 2. Well, I didn't label this. This was up at 4, but I'm just going to kind of guess that 2 might be about right here. And then what we want to do, if I move this up 2, it's probably going to be, if I move it up 2, is at 3. So remember when we draw this part of the graph off of this point right here, that you only want to go down as far as, not including one vertical distance here. So you have an asymptote. Your asymptote has actually shifted up 2, because the original asymptote was at y equals 0. So when we shift up, our new horizontal asymptote is at y equals 2. And then this other part of the graph would just come off in this direction. So because it's multiple choice, you'll probably be asked to, identify the graph of the function that best models g of x here. Okay. All right, returning to our review. What else did we learn this year? Well, we learned about compound interest formulas. We had 2 of them. This interest formula was used when we had a certain number of compoundings per year, and this formula was used if we had continuous compounding. The keyword there being continuous, we knew we would use the APERT formula. All right, it looks like 43 and 44, neither of them are problems in situations where we compound continuously. So both these problems would require this formula right here. And so, of course, you're going to have a calculator for that as well. All right, so I would just say probably for those problems that if you just if you kind of got stuck on them, try them on your own. But then just look at the worked out solutions, and I think it's pretty straightforward there. Okay, I'm not sure if you're going to have a continuous compounding problem. If you are, you'd use this formula. And if you're wondering, will you be provided these formulas? Yes, you will. So there's no formula sheets allowed, according to the department, on the final exam, and no notes as well either. I guess to take the sting out of that, just knowing that it's multiple choice hopefully will kind of help. All right, let's look at the next group of problems. Write the equation in its equivalent exponential form. All right, so we are presented with a log equation, and we want to change this to its equivalent exponential form. This is where we kind of went around the world. We started with the base on the log. It becomes the base on the exponential. And we took 3 and we raised it to the second power, and we said it was equal to 9. B cubed equals 64. And that would be the choice that we would make. 47 and 48 have us go from exponential to log form, so going backwards of what we just did. I usually start with the exponent, and I say 2 equals, this is the exponent equals, I throw in the log, and the base on the log is 5 because it's the base on the exponential, and then we have 25 here. All right, 49 through 51, evaluate the expression without using a calculator. Hey, it's multiple choice. It's up to you. You can evaluate these with a calculator, and that'd be fine. Okay, let's talk about the calculator. So some of you may have, a more sophisticated calculator where you have a template that you can just insert by pressing an appropriate keystroke. You're getting a template that has a blank here and a blank here, and you can just insert the 4 and 64. If you don't have that more sophisticated scientific calculator, which you can use, okay, on the exam, then what you have to remember how to find this answer on the calculator is the change of base formula. And the change of base formula was that we created a fraction, and in the numerator, you could put log, and then we took the argument, is what we call that, log of 64, and then we did divide by log of the base, log of 4. So a way to kind of remember that is 4 is low here, and in a fraction, in the denominator, you're low. So log of 64, log of the number divided by log of 4. Likewise, it doesn't matter what log key you use on the calculator to get this answer. You could use the ln key. So this is also going to be equivalent to ln, natural log of 64 divided by ln of 4. So I would just say that you just caution you on the calculator that parentheses could be critical here. So I would probably do an open parenthesis, and I'm going to do ln 64 and close the 64, but then go ahead and close the parenthesis again, and then divide. And in the denominator, it's probably not a big deal if you have a parenthesis around ln of 4, but just for good measure, you might want to go ahead and do that. ln of 4, close the parenthesis twice, enter, and the answer is 3. Without a calculator, what we did is we changed this to an exponential. We said 4 raised to what power is equal to the answer of 64. And what we did is we changed 64 to a power of 4. 64 is 4 cubed. And once you get the same bases, then the exponents have to be equal, and you do end up with x equals 3. All right, if you're going to do calculator, this would be log of square root of 12 divided by log of 12. Or again, you could use ln, it doesn't matter. Just be careful when you're entering square root of 12 as well. All right, otherwise you can change this to an exponential. Let's do that real quick. This would be 12 raised to what power is the square root of 12? Well, we have the same numbers, it's just the issue is the square root here. But if you remove the square root, it becomes a 1/2 power. So the 12s can be eliminated, and we get x equals 1/2. So whether you do the calculator or by hand, we should get 1/2. All right, I think we'll move on. You can check the worked out solutions for the algebraic work here without using a calculator or not. Okay, let's look at the next group of problems. Okay, so properties of logarithms to expand the log expressions as much as possible. Where possible, evaluate log expressions without using a calculator. Got it. I believe this was section 4.3. Yeah, where these problems came from. All right, properties. We had product to sum. So we definitely have a product here. We did difference to quotient. Quotient to difference, pardon me. Quotient means a fraction to subtraction, quotient to difference. And then here we had the power to factor property. So let's go ahead and split this up using the property. So log base 6 of 7 plus log base 6 of 3. And you could try and simplify these on the calculator to see if you get nice numbers. If these return ugly decimals, then you don't want to look for that answer. You don't want to, well, that answer won't be there because these are supposed to be done without a calculator. So this would be the final answer. All right, quotient to difference. So log base 7 of 7 minus log base 7 of x, high and low. The low goes behind the subtraction sign. This is equal to 1. 7 raised to what power is 7? Well, that is going to simplify to 1 over there. So the choice you're going to be looking for is 1 minus log base 7 of x. And when we have a power, we make it a factor, and we put the 6 in front. So 6 times log base 7 of x, and we're done with that problem. Okay, so for both of these problems right here, we're asked to solve the equation by expressing each side as a power of the same base and then equating exponents. Okay, well, 5 is a smaller number, so let's take 25 and rewrite it as a power. So 5 to the x equals 5 squared, same base. The result is my answer is 2. Solve the exponential equation. Well, I have the same base, so those will drop out, and I'm just left to put the two exponents equal to each other. So now I'll solve. I'm going to subtract a x on both sides. Hold on the screen. Subtract 5, subtract 5. So x equals 4 minus 5 is negative 1. Okay. All right. In this next group of problems, we've got 5 problems where we're going to solve these log equations. And then, okay, these were the problems where we had to be sure and always check our solutions because we do not want a negative number to fall after log. So if x was 3 and I added 5, that's a positive 8. That's fine. I just want to be careful that if I put a number in for x here and I add 5, if I get negative, I have to reject that solution. Okay, that negative number is not in the domain of the log expression. Okay, so we're going to solve these log equations and we're going to check our proposed solutions. All right, you might not remember, but let me remind you that when we solved log equations, we really had 2 strategies, and depending upon what was in the problem, determine what strategy we used, meaning this. Look at 57. Every term in this equation, this term and this term have a log with it. Okay, in 58, okay, I have 3 terms, 2 on this side of the equation, 1 on this, and all 3 of these terms have a log expression. They're log expressions. I'm going to use the same strategy to solve 57 and 58. Okay, and then I see that 62, okay, we have an expression here and an expression here, and they both have logs. What I've highlighted in yellow will be solved, those 3 equations, log equations, will be solved with one strategy. Look at the unhighlighted other 3 problems. Notice that 3 doesn't have a log expression, 7 does not, neither does 3. Notice that 4 does not have a log expression. So these 3 are going to be solved with the other strategy. Okay. So we'll at least do 1 of each of them, possibly 2 of each of them, but the ones that I don't do, again, you can check the worked out solutions. Okay, let's start with 57. Okay, and I'll put this back up here. All right, for this type of problem where you have log expressions in all the terms, we want to reduce each side of the equation to 1 log term. Well, I've got one log term here and one log term here. If I had multiple log terms, I'm going to have to use some properties to condense into one log term. Next thing we did is we removed the logs. Once you get one log expression on each side of the equation, you can remove the logs and you can set the arguments equal to each other and mathematically solve. So now I have this algebraic equation to solve. I'm already looking ahead. So this is about 2 1/4. Remember, before we say this is a solution, let's go back and check it. So go back to the original presentation of the problem. If I plug in a 2 1/4 here and add 5, this is a positive number, I'm good. If I plug in 2 1/4 here, multiply by 5, and subtract 4, this is still going to be a positive number here. So both of those positive numbers are in the domain. This is a good solution. Okay, let's look at, we'll look at 58 because there's a little more work going on in that one. On 62, it would be as easy as removing the 2 logs. I would put 9/1 and cross multiply and then continue solving. So I'll leave that one here, but let's at least look at 58. Okay, I'm going to get ready and writing 58 down. But look at the left-hand side of the equation. I have 2 log expressions that I have to work on. I have to condense those because if I'm going to be allowed to remove the logs, I can only remove 1 log from each side. I can't just decide to remove 2 logs here and 1 log there. That's not the way that strategy works. So here's the problem. I have got to condense these 2 log expressions. Well, I have a minus, so I'm going to go back to a fraction. So I've got log of, I've got a fraction. The first expression is 3 plus x. It goes on top. The minus means quotient, and I have x minus 5 here. And I still have log 3 here. I'm good to go. I'm going to remove the logs. I'm going to bring down this quotient. I'm going to set it equal to 3, but I'll make that 3/1. I'll cross multiply and then continue solving the algebraic equation. Don't forget to distribute 3 into both the x and the minus 5. That's a common mistake. So it looks like x is going to be 9, but let's go back and make sure that this x equals 9 does check. Okay, meaning we only want positive numbers after the log expression, and it looks like it does check, so it looks like my solution is x equals 9. All right, I'm going to go back now. I'm going to look at the highlighted green problems because they require a different strategy in solving those. Okay, we might as well just start with 59. Now, what's similar to the problem we just did here is even when I use this different strategy for 59, I can still only have 1 log expression on each side of the equation. So we're going to have to apply some properties here. And I'm not going to put the 2 in parentheses there. All right, we don't have a log over here, so let's condense these and then talk about how we're going to proceed. So plus means multiply, so I'm going to multiply these 2 arguments, log base 2, and then I'm going to have 2 times 3x minus 5. I will distribute that 2 in my next step, equals 3. We don't have a log over here to remove, so what we did is we changed this log equation to exponential. So we went kind of around the world. We said, okay, 2 cubed equals, and then all of this. And let's continue solving. That's going to be 8. Let me distribute the 2. And then I just continue solving this 2-step equation. Add 10. 18 equals 6x. Divide by 6. So x is 3. But let's go back and make sure and check 3 in here, and we do get a positive number, so that's a good answer. Okay, let's look at 60. Well, I only have one log expression. It's a natural log. I think I'm going to isolate. Let's isolate that log expression, get that ln of x by itself, and then do the around the world situation. So let's subtract a 3 to both sides. And I don't really need those parentheses there. That's going to be 4. Let's divide the 2. We got to isolate this log expression. So ln of x is equal to 2. You might remember that you could change ln to log base e of x. Or you could just think, well, there is an understood base of e there. Let's now change this to an exponential. So we isolated the log expression and then changed to an exponential. So we're going to get e squared equals x. And that's the actual answer, e squared. You could change it to a decimal if you want, but e squared is positive, and when I check it up here, I'm still good. So that's the answer. Okay, and lastly, 61. I would divide out the 3 first to isolate the log expression. So you're going to get 4/3 here. And then once you do, you can change this log equation to an exponential equation. It'd be 8 to the 4/3 equals 5x minus 9. And then use your calculator to assist you in continuing to solve that. So I think we best stop there. And in the next video, I'll pick up with problem 63.